Hi, hello. My name is Aparna and I'm here with you to help you through your physics class. Now, I'm sure that you've had enough of a taste of 11th grade physics to figure out that physics isn't exactly a piece of cake like it was for us in 10th grade. So physics is starting to get a little bit complicated, a little bit theory, derivations, too much. So now here, what I'm planning to do is, I'm not trying to make it fun or easy for you. In fact, well, there is a lot of ways in which physics can be fun, but that's more up to you than up to me. What am I here for then? I'm here to maybe make things a little bit easier to understand. Maybe explain the steps a little bit, take you through it a little slower than you would in class. Take you through the whole lot of it just a little slower, make it just a little easier for you to understand. So, and hopefully as we go along the way, me and you together, we can see the fun in physics. We can see how and where physics can be enjoyed, how physics can be fun, and hopefully we'll start enjoying physics. So let's start with 11th grade physics. Now the very first chapter in your textbook is about the physical world. Now, I found that to be a very, very interesting chapter because that chapter, when I was studying 11th grade physics, that chapter actually helped me to keep my interest for physics burning and alive. It made me see physics in all the different facets that you normally wouldn't see in our everyday lives or even in our classrooms. We look at physics through very specific points when we learn physics in class. But that first chapter, reading through that first chapter, which it's something that you need to do personally. Read through it personally. I'm not going to get into details about your first chapter, from which you can have questions, but it's more of a personal voyage there, where you find the joy, the fun in physics, and the absolute vastness, the huge scope that physics as a subject, as a discipline, travels through. Now that chapter carries a lot of points for you, such as the differences between classical physics and modern physics, the different kinds of physics, the areas that each of them cover, as well as the major forces, the basic points of physics, and what the forces that hold the entire universe together, from the microcosmic to the macrocosmic level. It gives you a brief glimpse of physics in all its glory. I know it sounds like I'm going on a little bit of exaggeration, doesn't it? But you should read that chapter, for it's fascinating, and read it with an open mind, ready to understand. Okay, let's move on from the grandeur of physics into more everyday matters. I'm going to show you a series of images, and I want you to tell me exactly what comes to your mind when you see this one. What is this image? A weighing scale. We're all very familiar with it. We go to the supermarket, buy vegetables or fruits, and we take it to the weighing scale to be measured. Now what's the next image? We have a thermometer. It could either be a thermometer used to measure room temperature, or it could be a clinical thermometer. And next, a stopwatch. What do we use a stopwatch for? To measure time. And next, this is a measuring tape. Now, these are all items that you're all very familiar with, things that we use in our daily, everyday life. And this daily, everyday part is exactly what we're going to talk about in today's class in detail. We're talking about units and measurements. Now, let's just say that you go to the supermarket, you buy your things, you buy fruits or vegetables, you take them to be weighed, you get the weight, you have a small little sticker giving you the measurement, giving you exactly how much your fruit or vegetable weighs, and you have how much the corresponding price on it. When I was in school, especially when I was in 9th, 10th, 8th, 9th, 10th, etc., I used to lose a lot of marks in maths, because I used to keep forgetting to write the unit after the number. I'd solve the whole problem, I'd come to the correct answer, and then I'd forget to write centimeter or kilogram. And I always used to lose mark, half mark, sometimes even 1 mark. And That was a very, very sad way to lose marks. And I never really understood how important writing that small 1 or 2 words there at the end is. But just imagine, suppose I say I am 160 centimeter. I'm just 160. What would you understand by it? I say I'm 160. It could be that I'm 160 centimeters in height, I weigh 160 kilograms maybe, or I weigh 160 anything. It could be any measurement, anything. It could allude to any number of things. But once I put that unit, centimeter, at the end of that number, 160, it means a very specific thing. It means I'm alluding to my height or any length. 160 centimeter becomes 160 becomes a unit of length of any kind. Now, the measurement of any physical quantity, just like this, as we've seen, involves comparison with some certain basic, arbitrarily chosen reference point. And this reference point that we use today is an internationally accepted standard. This is called a unit. Without unit, measurements as a whole do not make sense because what we measure acquires a meaning. What we measure acquires a meaning only when we add the unit at the end. The result of any measurement is expressed in terms of this numerical value followed by the unit. And this gives us the complete quantity that we are measuring. Now, we know that we have a large number of quantities in the physical world. We have length, breadth, we have distance, we have small areas. We have a lot of things to measure in the world around us, in the simple world around us. But, interestingly enough, the number of units that we need to measure this wide range of quantities is surprisingly very small. This is because a lot of these quantities are interrelated. And when they are interrelated, it means that a lot of them have a common reference point. And according to this common reference point, or according to one common basic quantity, quantity or the unit for that quantity, you can measure the other physical quantities. Now, the units for measurement are known as for these fundamental qualities or these base quantities, the things for which you have its own specific units, arbitrarily chosen, universally accepted units. These quantities are known as base quantities, and they all have their own specific units. And then we have those other quantities for which the units are given. They're basically derived from these base quantities, such as, for example, we measure length in maybe centimeter or meter. But at the same time, when we look at area, we have centimeter square or meter square, etc. So a lot of quantities depend on these base quantities to get their unit. They're known as derived quantities because their units are derived from these base quantities. Now, the complete set of these units, the base units as well as these derived units, together form the system of units. Now, when we talk about the system of units, let's talk about some of the more common systems, the names, the measurements that we're all very familiar with. Now, a lot of countries, before the universally accepted standard came into place, a lot of countries preferred to go for their own specific systems. And some of the more common ones followed across the world were the CGS system. And when we talk about the system of measurements, we look at the more common measurements. The basic common measurements which we use to devise a system is basically the 3 basic quantities, which are length, weight, and time. So we look at measurements, at units, at quantities, system of units according to the way that length, weight, and time are measured. And the earlier quantities include the CGS system, which is centimeter, gram, and second. And these were the common or the base units. They were the commonly accepted units. And then we have the FPS system. FPS was more prevalent in Britain rather than in most other parts of the country. And the FPS system stands for foot, pound, and second. Foot, pound and second were the units of measurement for length, weight and time respectively. And now the more common system, which we're all familiar with and which was later accepted as the international system, is the MKS system, which is the meter, kilogram and second system. Now, this system of units, which is at present internationally accepted for measurement, is the International System of Units, which is abbreviated into SI units. You've heard of the SI units, right? SI unit for time, SI unit for length, SI unit for mass. Now we have a fixed quantity for all the base values in the SI unit system, and according to this system we have all our conversions, we have all the values, we have all the physical measurement. Everything in the world that we know today has its base with the SI system, and this SI system has an equal value all over the world. Now let's go through, we talked about the base quantities. Let's talk about what the 7 base quantities are. We're going to talk about what the quantities are and what their SI units are and the symbol used for each of these. Now in your textbook there's a nice little box that gives you all these details in addition to some extra very interesting information regarding all these units, their symbols, what they specify, etc. You should take a look at that little box. It makes for very interesting reading. But well, we'll go through our major base quantities and their symbols one more time. We'll just go through it here once. Now the first quantity, as we've seen, is length, and length is represented by has the SI unit of meter, which is represented by the letter small m. Not capital M, small m. The capital and small usage of capital and small letters makes quite a big difference when you're denoting the symbols of these units. So meters is represented by a small m. Next, we've seen the 3 main quantities, which are length, mass and time. We follow the same order here. So we've length, meter, m. Next is mass, which is given to us by kilograms. Kilogram being the commonly accepted SI unit, standard international standard of unit of measurement of mass. And the symbol for kilogram, as we know, is kg. Very simple, easy to remember. And next we have time, which is measured in second and represented by S. Now these 3 are the very familiar ones, things that are easy to understand. The next 4 are the ones that we need to keep in mind, which we may slip on a little bit because we don't use it in our everyday lives as much as we do the other 3. The next one is electric current. Now electric current is measured in amperes, and ampere is symbolized through the letter capital A. The other 3 had small letters, while ampere has a capital A. And the next quantity is thermodynamic temperature. We're all very familiar with temperature, but in our everyday lives, we measure temperature in terms of degrees Celsius, or in certain cases, when we look at our clinical temperature, we measure it in terms of degree Fahrenheit. But the actual SI unit or SI unit of measuring thermodynamic temperature is neither of these. It's Kelvin, and Kelvin is represented with a capital K. Now the next quantity is the amount of substance. The amount of substance formed in or given in any given mass is measured in terms of mole. Chemistry should have given you a brief introduction into what the mole concept is, how many moles of a substance any given gram or any certain amount of a substance carries. You should have been given a brief introduction in your chemistry class. Now, mole is the SI unit for measuring the amount of a substance, and it's represented with the letters MOL. And the last quantity that we need to know is luminous intensity. Luminous intensity is measured in candela. Candela and represented with a small letter CD. Now, these are the 7 basic quantities from which all other quantities, all other terms of measurement that we know, measurement of everything in the world around us, in the physical world that we see around us, and the world that is beyond our thought. When we look at astronomical levels, astronomical figures, all of these are measured using these as the base quantities. Now let's look at some of them in detail. Let's start with length, measurement of length. Now, we've all been measuring length, small lengths, things around us since we were in grade school. Now, how do you measure length? You can either use a ruler, a meter scale, a measuring tape, etc. And you even have other devices for measuring greater lengths, such as kilometers. Now, a meter scale which is the more commonly used method or commonly used tool for measurement, gives you the measurement of lengths from 10 raised to minus 3 meter. 10 raised to minus 3 meter would be equal to 1 millimeter to 10 raised to 2 or 100 meter. So that's the area, or that is the range of a meter scale. But what about quantities, or what about something that's smaller than a meter, or maybe around a millimeter? How do you get the exact measurement of something that's small? We have other tools such as the vernier calipers and the screw gauges, which help us in measuring things such as maybe thickness of a copper wire, which is less than a millimeter. And for these we have the vernier calipers and the screw gauges, which you must have familiarized yourself with in your laboratories. Now, a vernier caliper is used to measure lengths up to an accuracy of 10 raised to minus 4 meter, while a screw gauge and spherometer can be used to measure lengths as less as 10 raised to minus 5 meters. But what about lengths that are even smaller than this? Or what about lengths that are even bigger? For example, we know how to measure up to kilometers, but what happens beyond it? We have thousands, 10,000s, we can talk about millions of kilometers. But how do we measure this? We don't have any tool or any equipment which will allow us to measure some things on such a great level. For example, I need to measure the distance between the earth or the point where I'm standing. Let's just take the earth as one single point. From the earth to, say, a distant star. How do you measure the distance between the earth and a star if you do not have any tools or any measuring devices for the same? In such cases, we have to refer to indirect methods of measurement. Now, using the meter scale, using the screw gauge, the vernier caliper, etc. These are all direct methods of measurement. Now we move on to the indirect methods of measurement, which we use for measuring distances which are too great or measuring lengths that are too small. Now, an important method in this is the parallax method. Parallax is one of the most important methods used to measure distances that are really great, like astronomical distances. Now we'll start with parallax. You saw how a parallax is made using a pencil with the wall as the background or as the reference point. How the change in observation points gives you the parallax, and the distance between the two observations gives you the basis. Now, we saw in an example, like we saw in the video, let's just say that suppose we're referring to, in the video we saw how to measure a planet. Let's say in the same way that we're taking maybe another star. We need to measure the distance from the earth to another star. And for this, we take as the basis for our measurements, we take 2 points of observation at the opposite ends of the earth, and the distance between these points A and B, which are the points of observation, AB, will denote with the small letter B. Now the distance from A to P, the star P, and from P to B will denote with the letter D, capital D. Now we have the angle formed between these two lines or between these two lines of observation as theta. We have theta as the angle between AP and BP. We have D as the distance of AP, and we have B as the basis or the distance between AB. We have to measure the angle between the two directions along which the planet is viewed at these 2 points. Now, trust me, our scientists today have the technology, have the devices, the extreme delicate sensitive devices required to make such measurements. So we get accurate measurements for these distances. And now we have our angle theta. Now let's just put things into perspective a little. The diameter of the earth is just less than 13,000 kilometers. And if you're taking 2 points on the opposite ends of the earth, then B will be quite close to the diameter of the earth, which amounts to around 13,000 kilometers. And the distance of the earth to the sun, which is known as one astronomical unit, the astronomical unit is the mean distance between the earth and the sun. Now this distance is nearly 150 kilometers, 150 million kilometers. And the distance between the earth and the nearest star to the earth that we know of today is Proxima Centauri, and Proxima Centauri is a part of the Alpha Centauri triple star system. And this star is more than 4 light years away. And 1 light year is equal to 9 trillion kilometers. So we're talking about distances that are that massive. So massive scale distances. And this is what we are attempting to measure. Now, as the planet or as the star that we are measuring is very, very far away, let's take B by D will be a value that is very, very, very much lesser than 1, which means that this implies that the value of theta is infinitely small. So now let's take, there are a lot of ways to go forth from this point. We could either use the trigonometry method to measure the angle, to measure the given distance, or we could use another easier, simpler method, the method given in your textbook. In the textbook, what we've seen is that they took the length AB as an arc for a circle of which P is the center and D becomes the radius. So now the radius we have AP is equal to BP in such a way that, now we know that when an arc AB subtends an angle theta at the center, we've learned that theta is equal to length of the subtended arc by length of its radius. Because the radian measure of a central angle of a circle is defined as the ratio of the length of the arc to the angle subtended. So from that we get the value of theta, we get the formula that theta is equal to length of the subtended arc, which is B, by length of the radius, D, from which we get B is equal to d theta, and D we get the value B by theta. Now B is a value that we know, it's a known quantity, and theta we've already calculated using our devices, using our ultra sensitive devices. So from these known values we can calculate the value of D, which is going to be a very, very high quantity. Because theta is such a small value, the value of D would be correspondingly as high. Now that gives us the measurement of very large distances. What about estimation of very small distances? Let's say something smaller than what the screw gauge can measure. The screw gauge measures distances up to 10 raised to minus 5 meter. What about something even smaller? Let's talk about the molecular level. How do you measure the size of a molecule? Now, there's a very easy experiment in which you get to measure the length or the size of one particular molecule, which is the one that we are commonly using in order to understand this method, is the oleic acid molecule. So now the size of a molecule is usually around the range of 10 raised to minus 8 to 10 raised to minus 10 meter. And for this, where even a microscope has limits, you need to use another indirect method. It's actually quite a simple experiment which we need to carry out with the oleic acid. Now let's see how it was done once. We saw that oleic acid is a soapy liquid with a large molecular size up to the range of 10 raised to minus 9 meter. First, we dilute this oleic acid in alcohol. We dissolve it, or we make alcohol solution with oleic acid twice, so that we dissolve 1 centimeter cube of oleic acid in alcohol to make a solution of 1 by 20 into 20 centimeter cube, which is the concentration of the solution that we have now. Now, we've dissolved 1 centimeter cube of oleic acid in 400 centimeter cube of alcohol to obtain a concentration of 1 part by 400, a very light concentration of oleic acid. Next step we saw is to sprinkle some lycodium powder on the surface of the water in a large trough and to put 1 single drop of the solution into the water. Now, this oleic acid, if dropped on water, spreads out to a thickness which we assume to be close to just 1 molecule. So we have a monomolecular layer of oleic acid spread across the water. And now, to understand why this happens, why oleic acid forms such a thin layer, and why oleic acid is specifically chosen to carry out this experiment, let's take a look at this. This is the chemical formulae, or rather the structure of the oleic acid. Don't panic, you don't need to learn this. This is just to help you understand better. Now we see that oleic acid is a very long molecule with a hydrophilic end and a hydrophobic end. Now, what is a hydrophilic and hydrophobic? What do these words mean? Hydrophilic basically means water loving, and hydrophobic means water hating. So the hydrophilic end is towards the bottom, where it will be immersed in the water, or where it will touch the water molecules, and the hydrophobic end extends upward. It stands up straight. So with such a structure, where the oleic acid molecules support each other and almost stand up straight, we can say that the thickness of the oleic acid forms a layer that is 1 molecule thick, in which case, when we measure the thickness of this layer of oleic acid, we get the size, the length of that 1 long molecule itself. Now let's see how we measure this. The drop we have seen quickly spreads into a thin, large circular film, which we assume to be of molecular thickness. This is the oleic acid molecules standing on their hydrophilic ends. We can measure the diameter of the circle so formed, and from the diameter, with that, we can measure the area of this drop. Now the area we take to be A, capital A. Suppose we've dropped n drops of oleic acid in the water. Initially, we determine the approximate volume of each drop, nV centimeter cube. Now the volume of n drops of solution is nV centimeter cube, and the amount of oleic acid in the solution will be nV into 1 by 20 into 20 centimeter cube. So this solution of oleic acid spreads very fast on the surface of water, and it forms a very thin layer of thickness which we can take to be T. Now, if this spreads to form a film of area A, centimeter square, then we can get the thickness of the film T to be equal to volume of the film by area of the film, which is equal to NV by 20 into 20 A centimeter. Now, suppose we have dropped n drops of this oleic acid solution in water. Initially, we determine the approximate value of each drop to be V. Let's give it a value V centimeter cube, which means that the volume of n drops in the solution is equal to NV centimeter cube, and the amount of oleic acid in the solution will be equal to NV into 1 by 20 into 20 centimeter cube, which we are dividing. Now this solution of oleic acid spreads very fast on the surface of water, and let's say that it forms a layer of thickness T. And if this layer has an area of A centimeter square, then we can assume that T is equal to volume of the film by area of the film, which is equal to NV divided by 20 into 20 into A centimeter. And with this we can get, with the values of N, V and A that we can find out, With this, we can get the value of T, which is equal to thickness of the film. And we are already assuming that the film formed by this oleic acid is monomolecular, which means that the entire film has the thickness of one molecule of oleic acid, which means that the thickness of the film is equal to the size, the length or the size of the molecule of oleic acid. So with that, we are able to figure out the size of the oleic acid molecule. Now, we've seen how we can look at objects of astronomical length as well as microscopic length, which means that the size of the objects that we come across in the universe, in the world around us, as well as in the universe around us, vary over a very wide range, from the size from the order of 10 raised to minus 4 meter to the order of 10 raised to 26 meter. 10 raised to minus 14 meter is the size of the tiny nucleus of an atom, and 10 raised to 26 meter is the extent of the observable universe. Observable underlined because the universe extends far beyond the limits of the science that we have today. Now, we have all these great ranges, but we cannot really measure all these ranges of lengths with the units that we have. So we've allotted some special units of measurement for these intermediate measurements, such as, we'll start from the smaller ones. We have the unit of 1 Fermi. Now, 1 Fermi is equal to 10 raised to minus 15 meters. Now, after 1 Fermi, we have angstrom. 1 angstrom is equal to 10 raised to minus 10 meters, and angstrom is a unit more commonly used to measure molecular sizes, etc. Now, after the 1 angstrom, we have the more common units: millimeter, centimeter, nanometer, millimeter, centimeter, meter, kilometer, etc. And then we go on to the larger scale, to the macroscopic scale. On the macroscopic scale, we have light year. 1 light year is equal to 9.46 into 10 raised to 15 meter. And this is the distance that light. Now we know that velocity of light has been unmatched by anything in the known universe today. And even light, with its great velocity, covers time of 1 year to cover a distance of 9.46 into 10 raised to 15 meter. Now this distance covered by light in 1 year is known as 1 light year, and it's a common term used in astronomical measurements of length, because we've seen how the nearest star to the Earth is around 4 light years, more than 4 light years away from the Earth, which means that even at the speed of light, it would take us over 4 years to get to the nearest star to the Sun. Now, after the light year, we have the greater unit called parsec. 1 parsec is equal to 3.08 into 10 raised to 16 meters. And this is a unit of distance and is equal to roughly around 3.26 light years. Now, measuring parsec is a little more complicated, where 1 parsec corresponds to the distance at which the mean radius of the Earth's orbit. Other units of measurement which we use in extreme cases for very small or very large distances include 1 Fermi. Starting from the smallest level, we have a Fermi, which is equal to 10 raised to minus 15 meters. And after the Fermi, we have angstrom. 1 angstrom is equal to 10 raised to minus 10 meter. An angstrom unit is the unit more commonly used to measure distances or lengths, range of lengths at the molecular level. Now, after angstrom, we also have micrometers, nanometer, micrometer, millimeter, centimeter, meter, kilometer, etc. And on the terrestrial level. Now, when we go beyond the surface of the Earth into the astronomical level, first we have the astronomical unit, or 1 AU. Now, 1 AU is the average distance of the Sun from the Earth, and it has an approximate value of 1.496 into 10 raised to 11 meters. need to understand the concept of AU as being the average distance of the Sun from the Earth, from the center of the Sun to the center of the Earth. Now, after that, we have the light year. I'm sure you've all heard the term light year. Now, 1 light year corresponds to the distance that light travels in 1 whole year. Now, we've learned that the velocity of light is unmatched by anything in the known universe. So even light travels the distance that even light requires to travel in a time of 1 year. This distance is known as 1 light year, and approximately we have a calculated value of 9.46 into 10 raised to 15 meters, the value of 1 light year. And on a larger scale, we have the value of parsec, where 1 parsec is equal to 3.08 into 10 raised to 16 meters, and it's approximately it's a unit of distance measured and used in astronomy, and it's approximately equal to 3.26 light years. Now, the calculation of parsec is has a little bit more of complicated theory behind it, where 1 parsec corresponds to the distance at which the mean radius of the Earth's orbit subtends an angle of 1 second of arc. Now, these are all the different measurements used for the more extreme measures, extreme range of lengths. And we've seen how some of these distances are measured through indirect means. Now, after we've looked at length, let's look at how mass is measured. Now, mass, as we know it, is the basic property of all matter. What is matter? Anything that has mass is known as matter. And mass is a fixed entity. It does not depend on temperature, pressure, location, or where the object is in space or any other fact. Mass of an object will remain constant whether it's on the Earth, whether it's on the Moon, or whether it's in outer space. Now, this is the distinction between mass and weight. Weight is dependent on the location of the object as well as external factors. Now, mass, the SI unit of mass is kilogram, and it's the more common unit used in the measurement of mass. We have kilogram, gram, milligram, etc. But when we look at a smaller level, at the atomic or subatomic level, kilogram becomes a very inconvenient unit because kilogram is too huge to cover the minuscule amount that we have of mass that we have in atomic or subatomic levels. In this case, we have another very important standard unit of mass. This is called the Unified Atomic Mass Unit, AMU, usually denoted with the letter U. Now, the atomic mass unit has been established for expressing the mass of atoms as 1 U is equal to the value of 1 atomic mass unit is equal to 1/12 of the mass of the atom of a carbon-12 isotope. Now, 1 U is equal to 1/12 the mass of an atom of carbon-12 isotope. Now, the mass of commonly available objects to us can be determined with a common balance like the one used in a grocery store. However, when we look at the large scale, at planets or at stars, galaxies, etc., we have a more complicated system of measurement which uses Newton's law of gravitation, and it's known as the gravitational method of figuring out mass. And for measurements of substances at atomic and subatomic particles, we have devices such as the mass spectrograph, etc., in which the radius of the trajectory is proportional to the mass of a charged particle moving in uniform electric and magnetic field. Through this, we can calculate the exact mass of charged particles such as electrons, etc. Now, with the mass of the objects that we've come across in the universe, in the known universe and at the subatomic level, have a greater range than the range of lengths that we looked at. In fact, the known masses vary across the order of 10 raised to minus 30 kilogram, which is the mass of an electron, to the huge mass of 10 raised to 55 kilogram, which is the approximate estimated value of the entire universe. approximate, and estimated being the key terms here of the known universe. Now, that's about mass. Now let's look at the final base, not the final base quantity, but the third of the three important base quantities that we looked at, time and the measurement of time. Now, time seems to be the most dependable, most permanent, set thing for people like us who live on terrestrial conditions. Now, to measure time, any time interval, we need a clock, any kind of clock. And what is a clock? Any phenomenon that repeats itself is termed as a clock. And any device that we use to measure time, it could be a clock itself, like the clocks that we have at home, it could be a wristwatch, or it could be any rhythmic, anything that occurs in periodic order at set intervals can be termed as a clock or can be used to measure time. Some of the common clocks or some of the common measurements of time, devices to measure time that science has devised till now, includes electric oscillators, electronic oscillators, we have the solar clock, we have the quartz crystal clock, we have atomic clock. And then for time intervals which are minute, which are barely minute parts of a second, we have the decay of elementary particles, which is measured using photographic emulsion techniques. And with this method, we can measure time intervals as small, as tiny, as minutely tiny as 10 raised to minus 16 to 10 raised to minus 24 seconds. That tiny time intervals can also be calculated using this new method of using photographic emulsion techniques through which we look at the decay of elementary particles. Now, these are all the more common techniques that we use to measure time. Time has for a long time been known as the one constant, the one thing that is unchangeable. But science as we know it, and particularly physics, changes at a breathtaking pace. And especially in the past century or so, we have faced tremendous changes in physics and in our ideas of physics, of the world around us. And time itself as a whole has ceased to be that permanent thing, that permanent, unchangeable fact, that unchangeable quantity that it used to be. Now we know through Einstein and his inventions, through his discoveries, through the theory of relativity, we know that even time is relative, that even time changes. And we have a lot of inventions. Every day that science moves forward, what we know about the universe changes, our perceptions shift, and we know more, we come across more. But all of these measurements that we do, we look at firm measurements on terrestrial levels, such as a couple of kilometers or a meter, something that we measure with absolute accuracy, as we might think. But all of these have a small margin of error. Now, what exactly is error? Error is not making the mistake. It's not a mistake as we know it. Rather, error as we know, error in scientific terms is the uncertainty. Is the uncertainty in readings, in measurement. It's the room. It's basically just giving room to make a little bit of difference, to make a little bit of maybe changes in measurement, to give you that precise actual measurement. It helps us to arrive at a precise actual measurement. Now, there is a lot about error as well as accuracy, precision of instruments, and the errors, the different kinds of errors that we make in our measurements, how they're dependent on us, on the scientist or on the person who's reading the observation, as well as on the devices used, etc. Now we have a lot of theory based on that. We have our calculations, error calculations, we have the different kinds of error which we need to compute, all of which we'll deal with in detail along with the next parts of your chapter, such as dimensional analysis, etc., in our next session as we continue our chapter on units and measurement. Until then, if you have any doubts on anything that we've covered today, if there is any point in the derivations, any point about the analysis, anything about what we've covered in today's class, which you feel you're not clear about, do let me know. I will get back to you with the answers to your queries as soon as possible. Hope you had a good day. Thank you.